Welcome to Crashcast Java, your go-to podcast for all things Java. I'm Victor, and joining me today is the brilliant Sheila. Today, we're diving into a crucial, yet often misunderstood topic in Java, the Java Memory Model, or JMM for short. Sheila, why don't you kick us off by explaining what the JMM is all about?
Absolutely, Victor. The Java memory model is essentially a set of rules that define how Java programs interact with computer memory, especially in multi-threaded environments. It was introduced to ensure that Java programs run consistently across different hardware architectures and operating systems. Think of it as a contract between Java code and the underlying hardware.
That's a great introduction, Sheila. Could you elaborate on why the JMM is so important, particularly in multi-threaded programming?
Of course, in multi-threaded programming, different threads can access shared data simultaneously. Without proper rules, this can lead to unpredictable results, data races, and visibility issues. The JMM provides guidelines to prevent these problems and ensure thread safety. It's like having a traffic system for your program's memory access. It keeps everything organized and prevents crashes.
I love that analogy. Now let's break down the key components of the JMM. We often hear about working memory and main memory. Can you explain what these terms mean?
Certainly. Think of main memory as a central library where all the books, data are stored. Working memory, on the other hand, is like each reader's personal desk. When a thread, our reader, needs to work with data, it creates a copy in its working memory. The JMM defines rules for how and when these copies are synchronized with the main memory.
That's a clear explanation. Now, we often hear about three important concepts in JMM: visibility, atomicity, and ordering. Could you break these down for our listeners?
Absolutely. Visibility refers to when changes made by one thread become visible to other threads. Atomicity ensures that certain operations are performed as a single, indivisible unit. Ordering defines the sequence in which memory operations must occur. Together, these concepts help prevent issues like race conditions and ensure thread-safe operations.
Thank you, Sheila. Now let's talk about a fundamental concept in JMM, the happens before relationship. What exactly does this mean?
The happens before relationship is a key part of the JMM that defines the order of operations across threads. It ensures that the effects of one operation are visible to subsequent operations. For example, if operation A happens before operation B, then the results of A are guaranteed to be visible to B. This relationship is crucial for maintaining consistency in multi-threaded environments.
That's really helpful. Now let's discuss some practical aspects. The volatile keyword is often used in the context of JMM. Can you explain its significance?
Certainly, the volatile keyword is like a special flag that tells Java to always read this variable directly from main memory and always write it back to main memory. It's useful for variables that might be accessed by multiple threads. However, it's important to note that while volatile ensures visibility, it doesn't guarantee atomicity for compound actions.
Great point about atomicity. That brings us to synchronized blocks. How do they fit into the JMM?
Synchronized blocks are a powerful tool in the JMM toolbox. They not only ensure that only one thread can execute a particular code block at a time, but they also create a happens-before relationship. When a thread exits a synchronized block, it guarantees that all the changes made inside that block become visible to other threads that subsequently enter a synchronized block on the same object.
Excellent explanation, Sheila. Now, as we wrap up, could you share some common pitfalls and best practices related to the JMM?
Absolutely. One common pitfall is assuming that all operations are atomic. They're not. Another is relying solely on volatile for complex thread interactions. As for best practices, always use proper synchronization mechanisms like synchronized blocks or Java util.concurrent utilities for shared mutable state. Also, minimize shared mutable state where possible, and when you do need it, document it clearly for other developers.
Thank you, Sheila. This has been an incredibly informative discussion about the Java memory model. To recap, we've covered the basics of JMM, its importance in multi-threaded programming, key concepts like visibility and atomicity, the happens-before relationship, and practical aspects like the volatile keyword and synchronized blocks.
Absolutely, Victor. And for our listeners who want to dive deeper, Here are 3 advanced topics related to JMM: the Java, util.concurrent package and its atomic classes, the concept of memory barriers, and the intricacies of the Java fork join framework.
Excellent suggestions, Sheila. And that brings us to the end of today's episode of Crashcast Java. We hope you've enjoyed this deep dive into the Java memory model. If you found this helpful, please subscribe to our podcast for more Java insights. Until next time, happy coding.